Ever been at a game and seen a pitcher throw a ball that just seems to, well, break the laws of physics? Today, we're going to pull back the curtain and look at the amazing science that makes those wild pitches possible.
I mean, seriously, how does a pitcher make a ball swerve in mid-air like that? It looks like some kind of sorcery, doesn't it? But nope, it's not magic. It's something way cooler. It's science.
That's right, you can forget about smoke and mirrors. The number one secret, the absolute key to making a ball curve away from its path, is spin.
Okay, so let's get into it. The main scientific principle we're talking about here is called the Magnus effect. Now, I know that sounds like a super complicated, high-level physics thing, but I promise you it's actually pretty simple once you see it in action. Let's break this down. The TLDR version is this. A spinning ball drags air around with it, pushing that air to one side. And for every action, there's an equal and opposite reaction, right? So the air pushes the ball the other way. Think about it like this. You're in a swimming pool and you start spinning around. You're pushing water away from you, and what happens? The water pushes you back. A baseball is doing the exact same thing, just with air. And just so we're on the same page, force is just a fancy word for a push or a pull, spin is just the direction the ball's turning, and the wake is that messy trail of air the ball leaves behind it. See? Not so bad.
And here's a little fun fact for you. We call it the Magnus effect because a German physicist named Heinrich Magnus officially described it in 1852. But get this, Sir Isaac Newton, yeah, that Isaac Newton, had already figured it out and written about it way back in 1672. He was literally centuries ahead of his time.
So we know what the Magnus effect is, but how does it actually work in a game? Well, let's look at how this one effect is responsible for two of the most iconic pitches in baseball, the fastball and the curveball. Okay, check this out. It's all about the direction of the spin. A fastball has backspin, which means the top of the ball is spinning back towards the pitcher. This creates an upward force that actually fights against gravity, making the ball drop way less than you'd expect. It gives it that rising look. Now, a curveball is the total opposite. It has topspin. The air pushes the ball down, making it work with gravity and drop like a rock, sometimes an extra foot or more. It's the same science, just flipped upside down.
So how do pitchers get the ball to spin in these different ways? It all comes down to the grip and the release. For that classic fastball, a pitcher usually puts two fingers across the seams and kind of pushes down as they let go, creating that backspin. For a curveball, they'll grip it differently and then snap their wrist down at the last second to get that nasty topspin. And it's not just baseball. In softball, a pitcher will snap their wrist to create side spin, making the ball curve left or right.
Okay, so we've established that spin makes a ball curve. But what happens if a pitcher throws a ball with almost no spin at all? You'd think it would just fly straight, right? Well, this is where our story takes a little plot twist, because there's another force we need to talk about. An aerospace engineer named Bart Smith once said the baseball is the most fascinating object ever made by humans. And you know what? He's got a point. Because it's not just a smooth ball. It has those iconic 108 red stitches, the seams. And those seams are the key to a whole different kind of pitch.
All right, stick with me here. As a ball flies through the air, it has this super thin, invisible layer of air clinging to its surface. Scientists call it a boundary layer. Now, when the ball is smooth and spinning, that layer stays pretty even. But the raised seams on a baseball act like little speed bumps. They can trip up that layer of air, causing it to peel off one side of the ball sooner than the other. When that happens, the ball gets an unpredictable push and starts to wobble all over the place.
And all of this brings us to what might be the weirdest, most unpredictable pitch in all of sports, the knuckleball. So let's do a quick pop quiz to see what you know. Ready? True or false?
Okay, pencils down. Let's see how you did. Number 1, knuckleballs spin super fast. That is false. The whole point of a knuckleball is to have as little spin as possible. Number 2, a baseball's seams can mess with the air flowing around it. That is absolutely true. That's the secret sauce of the knuckleball. And finally, number 3, the Magnus effect explains a knuckleball's movement. That is false. Remember, the Magnus effect needs spin to work. With a no spin, it's all about those seams tripping the air.
And hey, this whole seam science thing isn't just a baseball trick. In the game of cricket, bowlers use this exact same principle. A cricket ball has one big seam running down the middle, and they'll polish one side of the ball while leaving the other rough. By angling that seam just right, they can make the ball swing through the air, curving left or right to fool the batter. So we've covered the physics of spin with the Magnus effect and the wild science of seams. We've learned a lot. But after all this science, what do you think is the single most important part of becoming a great pitcher?
Well, softball coach Emily Richardson says it best. The number one rule: practice, practice, practice. You can know all the physics in the world, but as she says, it takes a lot of time and effort to learn how to do it. There are no shortcuts to greatness. You got to put in the work. So there you have it. You now know the science behind a blazing fastball, a knee-buckling curveball, and even that fluttery, unpredictable knuckleball. The knowledge is officially yours. So the only question left is, which pitch are you going to master first?